Section 7-3 is on other differential equations. The objective of this section is to write and solve differential equations and use the solution as a mathematical model to make predictions. Now, if you recall in the last section, we were solving differential equations, and in the last section we saw that the differential equations that we were working with were exponential growth and decay problems. And because they were all exponential growth and decay problems, that meant that for each of those problems, the differential equation that you started out with was the same every single time. And that also means that as you go through and solve that differential equation, that your solution at the end is the same equation. It's in some sort of an exponential function at the end. And so that was nice that they all started out the same and they all ended the same. However, in this section here, we're going to find out that's not going to be the case. We're going to be looking at other types of differential equations. So the important part of this is going to be that you can actually read that problem, pull out the differential equation from the description of that problem that they give you, then be able to follow those same steps you followed before to solve that differential equation, and then get your solution to that differential equation at the end. All right, so let's take a look at an example. Example 1 here on page 234 says the following. This is the tin can leakage problem. It says, suppose you fill a tall tin can with water and then punch a hole near the bottom with an ice pick. The water leaks quickly at first, then more slowly as the depth of the water decreases. In engineering or physics, you will learn that the rate at which water leaks out is directly proportional to the square root of its depth. That right there was the differential equation. Suppose that at time t equals 0 minutes, the depth is 12 centimeters, and dy dt is equal to negative 3 centimeters per minute. So they give you an initial condition there at the very end. All right, look at part A. Part A says to write a differential equation that states that the instantaneous rate of change of y with respect to t is directly proportional to the square root of y. That right there is the same thing they told us in the problem set up there. And they also want us to find the proportionality constant. So let's start out by defining our variables here. They actually defined them for us, but I just want to write them down. They told us that y is the depth. So y is equal to your depth. And they're measuring the depth there in centimeters. And t is our time. And they're measuring our time, in this case, in minutes. Again, even in this problem, even though they gave you that, I'd still suggest you write those down just so you're clear on what your variables are, what they represent, as well as what the units are. All right, so part A, write the differential equation that states the following. The instantaneous rate of change of y with respect to t. Instantaneous rate of change of y with respect to t. That's dy, the instantaneous rate of change of y with respect to t is dt, or over dt. All right, instantaneous rate of change of y with respect to t is, so that means we're equal to something, is directly proportional. So directly means we're multiplying by something. Proportional means it's some constant times some other value. So it's going to be constant k times some value. Directly proportional to the square root of y. To the square root of y. So we're multiplying by the square root of y. Okay, so there's our differential equation. Notice it looks similar to the ones that we saw back in the last section. The difference here is that instead of being just y over there on the right, it's the square root of y. Which, with that being the case, that means our antiderivative here when we go through this is going to be a little bit different. And so therefore the solution is going to be different. It's not necessarily going to be an exponential function when we get done here. Okay, in fact, we're going to see it's quite different. All right. They wanted us to find the value of k as well. So we got the differential equation written down. They want us to find the proportionality constant. So the initial condition they gave us there was that when at t equals 0 minutes, that the depth, that's y, is equal to 12 centimeters. And the rate, dy dt, is equal to negative 3 centimeters per minute. All right, so there's our initial condition. We're going to take that and plug it in. Now, time t equals 0, we won't use that right now. We'll use that later. But I have a y in my equation here, in my differential equation, and I also have a dy dt in my differential equation. So let's substitute in for those. So dy dt is negative 3. That's equal to k times the square root of y, which is 12. And so let's solve for k. K turns out to be, dividing by the square root of 12, we get a negative 3 divided by the square root of 12. Okay? And if you want to, you can actually find out what that constant is here, or I should say an approximation for it here. We'll do that on the calculator. If we take a negative 3 and divide it by the square root of 12, and I'm going to store that into k actually while I'm doing this because we can use that later than in our calculations, we get a negative 0.866. It's approximately a negative 0.866. And you can decide to write this either way in your problem from this point forward. If you want to write it as negative 3 over root 12, or if you prefer, you can write it as the negative 0.866, since now we found it's equal to that value. But the key is, as you do the calculation, don't use this rounded value to answer questions later on. Make sure you keep as much precision as you can, so make sure you've either stored it in your calculator like we did, or you're actually using the negative 3 over root 12 for that k as you're doing that calculation. Let's write down what our differential equation is then. So dy dt is equal to, I'm going to go ahead and write it as negative 3 over root 12. If you want to write it as the negative 0.866, that's fine as well. And then it's times not y, but it's the square root of y. So there's our differential equation. All right, let's look at part B. Part B is where it really is going to involve the work in this problem. Part B says to solve the differential equation to find y as a function of t. And then use the given information, that's the initial condition we just used, to find the particular solution. That is, you'll be able to find out what the c is. When we integrate, we'll get a plus c, of course. And then what type of function is this? Okay, so let's look at part B here and solving this differential equation. Remember, the technique that we use here is called separation of variables. If you remember the name of it, it probably helps you remember the first step. Separation of variables, separate your variables. Get the y's on one side and the t's on the other side. All right? And the fact that you have dt in the denominator here on the left side, let me just circle that, tells me that I have to move that guy over here to the right. I got to get everything, or I should say, I got to get my differentials out of the denominator. So the fact that I've got dt in the denominator on the left side means I need to move it to the right, which means then that square root of y has to move over to the left. So we'll divide by the square root of y, we'll multiply by dt. So if we do that, we end up with dy divided by the square root of y is equal to the negative 3 over the square root of 12 times dt. All right, so we've done our separation of variables. Remember, we do need to integrate this, so I'm going to rewrite what we have on the left side just so that it'll be in a form that I recognize for finding an antiderivative. Dividing by the square root of y. Well, dividing by the square root means that, or excuse me, I should say taking the square root means that that's the same as raising it to the 1/2 power. And dividing by that quantity means it's the same as moving that to the numerator with a negative exponent. So I can rewrite this as y to the negative 1/2 dy. Again, the negative part is the fact that's in the denominator. The 1/2 is the square root. That's equal to a negative 3 over the square root of 12 times dt. All right, so there's our differential equation. And it looks like we are all set to solve this differential equation. We solve it by integrating both sides. So I'm going to put my integral sign in here and integrate both sides of this. So on the left side here, you've actually got a power function, so follow your power rule. Your power rule says you add 1 to the exponent, so that's y to the 1/2, and then you multiply by its reciprocal out front, so that's going to be 2 y to the 1/2. And on the other side, you just got a constant times dt, so that's going to be the constant, negative 3 over the square root of 12, times your variable, which is t. And don't forget, when you integrate, you always get a plus c there. All right. Now, you can wait till a little bit later to find the value of c if you want to. The tricky part is if you wait till later, you might have to come back to a previous step to figure out whether it's a plus or a minus. Sometimes when you go through solving this thing, you end up squaring, which is what we're going to have to do, and then you introduce some extraneous solutions there that you got to figure out which one's the right one. So I'm going to, at this point, find the value of c, and I'd suggest perhaps that's the best way to do it. I know we didn't do that in the last section, but for these types of problems, I would definitely suggest you find this value of c as quickly as you can. So we're going to replace t with 0. Let me go ahead and write actually that down. T is 0, y is equal to 12, and we won't use this, but negative, excuse me, dy dt is equal to a negative 3. Again, we don't need that value for this part of the problem. We just need to know that when time is 0, y is 12. So let's substitute that in. So we end up with 2 times y is replaced with 12 to the 1/2. That's the square root of 12, realize. That's equal to a negative 3 over the square root of 12 times t is 0. That's nice. And that's equal to c. So this guy right here is gone because you're multiplying by 0. So that's 2 square roots of 12 is equal to c. So we found our value of c. So we end up with 2y to the 1/2 is equal to a negative 3 over the square root of 12 times t plus 2 square roots of 12 is the value of c that we just found. All right, now our goal here, remember, is to find out what y is equal to. So we've got a few more steps here. So I've got to divide by 2 to get rid of the 2 over here. So I've got y to the 1/2 is equal to, I'll write this as a negative 3 over 2 square roots of 12 times t plus, when I divide this second term by 2, I'll get just the square root of 12. And finally, to get rid of the 1/2 power there, we take and square both sides. Remember, to do this, we're actually raising both sides to the reciprocal of this exponent here. So I need to raise both sides to the reciprocal of that. That's raising it to the 2 over 1, or the second power is what I've got to do. Okay, so when I multiply those exponents, I get 1, which is what I'm looking for. So we end up with y is equal to, it's going to be a negative 3 over 2 square roots of 12t plus the square root of 12 quantity squared. And there's our equation for y. Now, it might not be in a form that you recognize that type of function, but realize what you have here is a linear function. It's in the form of m times t plus b there. You've got some constant times t plus some other constant, and you're squaring that. I know if I take a linear function and square it, I get a quadratic function. And if you wanted to multiply this out and see the quadratic function there that you end up with, you could certainly do that. In fact, maybe we should just do that so you can see what you end up with. If we square this thing, negative 3 over 2 square roots of 12, that would turn out to be 9 over 4 times 12. That's 9 over 48, which we could simplify squared. Excuse me, 9 over 48 times t squared, plus 2 times the negative 3 over 2 square roots of 12 times the square root of 12. Thinking maybe I should actually just write this out here and worry about simplifying this in the next step. Let me do that, just so we're clear on what we're doing. We're taking the negative 3 over 2 square roots of 12 and squaring that. That's times t squared. And then we add that to 2 times the first term, which is negative 3 over 2 square roots of 12, times the second term there, which is the square root of 12, times your t. And then finally add on the square root of 12 squared. And that one's not too bad, hard to figure out, but we'll write it out that way for all this. And so what we end up with then, we already did this a second ago, but you end up with 9 over 48, which reduces down to 3 over 16 actually if you divide by 3, so I'll do that. 3 over 16 t squared. And then this middle part here, middle term here, the square roots of 12 are going to cancel out. In fact, so are the 2's here. So you'll end up with a minus 3t. Let me actually write it as subtracting 3t. And then the square root of 12 squared is 12. Okay, so that's what y is equal to. I think that makes it obvious that we are talking about a quadratic equation then here. So let's make sure we answered their question. We solved the differential equation, used the information to find the particular solution. We got that. We figured out what c was equal to, our constant of integration. And then what type of function is this? Well, this is clearly a quadratic function. All right, that's part B. And if I scroll back up through this, you can see that that's definitely the part of the problem that takes the most work here usually to get to that point. Quite a few steps in order to get to that, but there's no way knowing from the very first thing you write down there what type of function you're going to end up with until you go through those steps to find out that it's a quadratic function. You'll also notice that it didn't change. The equation, differential equation that we started out with didn't look much different than the problems you saw in the last section. It was the square root of y instead of y. And yet, instead of being an exponential function, it's a quadratic function. All right, look at part C. It says to plot the graph of y as a function of t, sketch the graph, consider the domain of t in which the function gives reasonable answers. Okay, so let's punch this into our calculator here. I'll go ahead and punch in the simplified form. Let me just scroll down so I can see both of these at the same time. Oops, it went off my screen though. Let me try that again. All right, so let's punch that into y1. So we've got 3/16 x squared minus 3x and then plus 12. And for a window here, again, we've punched this can with this ice pick, and it's going to start draining out. And we know that the depth starts out at 12. I guess I don't know for sure how much time it's going to take for it to drain completely out. So I'll go from 0 to, let's say, 30 seconds. We'll see what that gives us for a graph. We might need to change our window there slightly. But for our y values, I know that it starts out at 12 and it's going to go down to 0. I mean, that's the liquid draining completely out. So if I go from 0 to 12, we can graph this. In fact, I'm going to go to my table and just have it help me figure out what a decent range or decent domain for this is going to be. We'll start it out at 0 and we'll have it change by 2. And let's just see what we end up with here. So it starts out at 12 like we said and drains to, okay, after 8 seconds, we hit 0. It's all gone after 8 seconds. So let's change our window then from 0 to 8. We'll set a scale of 1. You'll notice, by the way, that after 8 seconds, all of a sudden this thing starts going back up. The function does. But of course, that doesn't make sense in our problem. It's not going to start filling back up with water. All right, and consider the domain, and I guess we should indicate the domain here since we've got a graph of it now, and we can consider the domain. The domain here, for what makes sense, is that t has to go from 0 to 8. 0 to 8 minutes. All right, the last part of this problem says to solve the equation from part B algebraically to find the time it takes the can to drain, and compare your answer with the time it would take the can to drain at a constant rate of a -3 centimeters per minute. Well, I guess we've kind of already seen that answer with the graph we just looked at. We saw that it was drained after 8 seconds, so we already have kind of a heads up as to what answer we're looking for. But let's see if we can actually come up with that. You've got a quadratic equation again. So for part D, we've got our quadratic equation of 3/16 t squared minus 3t plus the 12. And we need to find out when it's completely drained, which means your height, your y value, is equal to 0. Let y equal 0. Okay? And so if we want to solve this thing algebraically, probably the easiest thing to do is to get rid of the 3/16 that's in front of this. This is a quadratic equation, so obviously there's lots of ways you can solve this, including quadratic formula. You could even graph this thing. They said to do it algebraically, so we're going to try to factor this thing. So let's factor out a 3/16, and you'll be left with t squared. And when I factor out a 3/16, when I take 3 and divide it by 3/16, that leaves me with 16 minus 16t. And when I take 12 and divide out 3/16, that's going to leave me with 64. 12 divided by the 3 gives you 4 times the 16 is how we're getting the 64 there. And we want to set this equal to 0. And so yeah, this actually factors pretty nicely there now. This actually is a perfect square here. We have t minus 8 times t plus 8, or excuse me, times t minus 8. It's a perfect square, or t minus 8 squared, however you want to write that. So it looks like the solution to get a value of 0 out of this thing is that t has to be equal to 8, and that's in minutes. And that's exactly what we just found there from the graph. We saw that, actually it was the table that gave us that, but we saw it in our graph as well, that at 8 minutes, the can was completely empty. We hit 0. All right, those are the types of problems you're going to see in your assignment. And those are the types of problems that you definitely need to know how to solve. You need to be able to set up the differential equation from the problem, be able to read the problem, and be able to figure out that this is the differential equation they're giving us. And once you have that, be able to separate your variables and solve that differential equation. This is the heart of the problem here. You got to be able to go through all those steps and understand how to solve that differential equation. There's a lot of algebra involved there, very little calculus, to be honest with you. That very first step of this, let me scroll back up here, where we find the antiderivative, that's the calculus. There's one step there of calculus. The rest is algebra. And then finally, once you get that, you should be able to graph it and then perhaps answer some questions about that particular problem. Those are the types of problems you need to be able to work with in this section. That's as far as we're going to go right now.